sorry, give me one moment. I'm going to find where keynote is.
Yes.
Yes? All right, great. All right, so today we're going to talk a little bit about our project Espaloma, which is end-to-end differentiable construction of molecular mechanics force fields. So I've been talking about this for a lot during the previous lab meetings. But I think for the past few weeks, we got it to a point where we can actually use it. So just a little bit of background again. There are generally two types of models, traditional models that people use when it comes to simulate molecular or biomolecular systems in silico. One kind of method is quantum mechanics, which is very slow but very reliable. It is considered it's the gold standard in this field. And the other is molecular mechanics. So it's very fast, but there are a lot of assumptions that people make, and it's generally considered as a heuristic physical approximations. Recently, there is this new type of method people call machine learning potentials. So basically, they just have a very sophisticated functional form, and they would fit that to the quantum mechanics generated data. And afterwards, it will be a model that's a lot faster than QM, but still the disagreement between QM and machine learning potential could be around like less than half a K-cal per mole or so. So it would be just a fast surrogate. Now, the state of the art of machine learning potential is that it's not quite there on the upper left corner. So the speed of machine learning potential is still like 100 times or 1,000 times slower than traditional MM, although it's a lot more accurate. So on this design space, we're wondering whether there could be a type of model that's much, much, much faster, not much slower than the MM, but slightly less accurate than the SOTA machine learning potentials. All right? And this is basically the whole idea of Espaloma, where we started in the design space. So machine learning potentials, they really start from a QM perspective, but now here we start from a MM perspective and see what is wrong with MM. So MM, there are a lot of heuristic assumptions and approximations encoded in an MM model, especially in the bonded part. So it separates the n-body energy into the bonded part into the bond angle and torsion energy, which are either a simple harmonic form or a Fourier expansion of some angular functions. So the way MM works is that it will take an n-body system and will compute all the relative geometry values, geometry quantities here. For example, the R in the bond, the theta in the angle, or the phi in the torsion, which is just the dihedral angle, right? And everything else, for example, the KR or not, K theta naught, and K theta n, and the phases, they are all considered as constants or they are fixed during the simulation. So we call the set of R, theta, and phi, we just abstracted as a set of X, meaning the geometric quantities or entities, whereas the R theta, the KR are not, K theta, theta naught, and K phi, which is the torsion force constant, and phi naught, which is the torsion phases, we abstract them as a set of VFF, which is the force field parameters. So if we want to have a good force field, then basically what we need to do is to optimize this VFF force field parameters. And this is hardly anything new. People have been using basically an MLE estimate or something like that, or an approximation thereof, to find an optimal set of VFF force field parameters. The way they do this is to just have a set of parameters, calculate the energy using the set of parameters, and from this energy you can derive either forces or you can derive physical properties, and you'd minimize the disagreement between that object and the reference from either physical property data or quantum mechanics. However, there is one little thing here. So you need to start with a initial set of parameters. And whenever you optimize, you only optimize the parameters up to the assignment parameters to the atoms. So what this kind of scheme is not optimizing is what we call atom typing. So what is atom typing? In short, atom typing is a set of rules that people apply to atoms so that certain atoms and thereby certain bonds and angles and torsion would be forced to share a same set of parameters. So in the beginning phase of this, how would you distinguish between different atoms? We would use a basically lookup table. So we'll say something like, if you are a sp2 carbon and if you're connected to either oxygen or sulfur with a double bond, then we shall call you atom type number 1 or atom type C. Right. If you look at this table, and by the way, this is the table from GAF2, you will realize that there are only 3 things that it is considering. The first is the node attribute. What kind of carbon you are, what kind of nitrogen you are, what kind of hybridization. So it's basically just hybridization and elemental identity. And the second of all is the number of neighbors, right? If you look at 9 versus 11, then the only thing that's changed, or 8 versus 10, the only thing that's changed is really just the number of neighbors. And finally, it's the neighbor attributes, right? Whether you are a double bond O or double bond S or sp2, sp3s, etc. So as long as you can summarize these three parts, then you would be able to, according to this atom typing scheme, assign different identities to different atoms, right? So if you want to optimize this chemical environment realization part, then perhaps what you need is an optimizable hash function from the node attribute and the number of neighborhoods and neighborhood attributes to some sort of node representation, right? So we tend to call, well, in graph theory lingo, we tend to call the number of attributes and a number of neighbors and neighbor attributes. We would usually together call them neighborhood multiset, meaning the identity and the number of each neighbor. So we could denote this as N and V, where V is the node. So if you look at the equation on the right-hand side, this is basically the functional form we would be looking for if we want to optimize this chemical realization part. And you would soon realize that this is just the master equation of graph neural networks. So the problem became, okay, can we use graph neural networks to come up with atom representations and group them together? And from there, we can come up with torsion angle and bond parameters in a similar fashion with traditional force fields. So this is what we did in this framework, which we call extensible surrogate potential optimized by message passing, or Espaloma. Evidently, you just start from a chemical graph. There is no geometry. You abstract as a topology graph, which you can throw in a graph neural network, which would give you some atom embeddings. So after you have these atom embeddings, you would pull them together in a symmetry preserved pulling way so that you would have bond, angle, and torsion embeddings. More on that later. After we have all of these representations for atom, bond, angle, and torsion, you would have a very simple feed-forward neural network to come up with all of the atom, bond, angle, and torsion parameters. And so this is your entire set of VFF, and then you already have it. And the only thing that you need to do is to throw in geometry and you will get energy. You can take derivative of energy to get forces. You can use those derivatives to guide your Monte Carlo to have trajectories, and from trajectories you can get physical properties, etc., etc. So it all starts from the energy here. All right. So this package is pretty much still in development, but you can actually use it. You can fit an entire force field in less than 50 lines of code, and this code will run for like 3-4 hours, and voila, you will just get a force field, and you can serialize that. That replaces, I don't know, tens or hundreds of engineer years of work. And it's worth mentioning that it is all very modular. So if you would take a brief look at it, the code basically does what it does is that it will You will grab a data set, define some representation regarding the atoms itself, and then define some sort of pooling to come up with the bond angle and torsion parameters. Afterwards, you specify the metrics. So here we are fitting on the U and UREF, which is the predicted and reference energy on level G, and we're also minimizing Q and QREF, which is the predicted and reference charges, and one, which is the node level. So after you have all of these metrics, you just throw them together in a utility script, and we'll just train for a certain number of epochs, and you just have this model. And so this technically is a function null. So if you input a molecule, then the model would give you a full force field. Right, but before we do any of that, let's take a step back and examine whether our assumptions along the way have been valid, right? So we sort of hypothesized that, okay, graph neural networks can do better than, or can at least do as good as a traditional atom typing. Now, this is very hard to prove theoretically, because already we know that graph neural networks can do as good as a Weisfeld-Lehmann test, because the legacy atom typing rules are a little bit too messy. In a sense, it's very hard to conclude whether Weisfeld-Lehmann test could fully recover atom typing rules. So here we test experimentally or empirically how graph neural networks is able to refit traditional atom typing, and looks like it's doing an okay job. The overall accuracy is somewhere around 99%, and where it screwed up are the places where a human expert would sometimes get confused as well. For example, the CCCA confusion, it happens a lot in the molecules where it got wrong. It's basically just either a aromatic carbon or an aromatic carbon in a phenol system. So it's like another leaf in the tree. All right, so having established that we can sort of fit a traditional atom typing scheme, then we would move on to fit the bond angle and torsion parameters. Right, so if you look at the legacy force field, you'll realize that, okay, the bond length and bond K, which is force constant, are determined incredibly simply, right? So there is an AND operation that look at its two composing atoms, and there's a dictionary lookup that associate numbers to this class of bonds, right? Now we know that neural networks can do logic operations and they can look up a dictionary. It is only reasonable to assume that it can, once we have the atom representation, it's fairly easy to come up with atom to bond parameters. And the same thing goes for angles and torsions. Right, the only thing that we need to pay attention to is that there is this mirror symmetry that we need to respect. So it doesn't matter how you number your bond. If you have a bond E01, then it doesn't matter if you order the blue one as 0, red one as 1, or it's a purple, or the purple one as 0, the blue one as 1. It shouldn't change the parameters. So the same thing goes for angles and torsions. That's the only symmetry you need to care about. Now, in this paper, there's a sort of no-brainer way of doing this, is that one of the most expressive way of respecting permutation is that you can just grab any non-permutation invariant function and push your input with all of the permutation into this function and then average them. It's one of the easiest way to get a permutation invariant representation. So this is what we adopt. And then since we only need to care about this mirror symmetry, so the permutation is actually just going to and from, right? So not atom 0, atom 1, and atom 1, atom 0. You only need to enumerate twice. Now, so there's another tricky bit of this, is that harmonic functional terms are a little bit naughty to play with. if you look at this, you'll realize that the derivative of the potential energy with regard to K and to B are of drastically different functional form. So if you optimize these, at some region there are no signal for K at all. So it would either blow up or miss the target or diverge, whereas some regions doing okay. So we know that neural networks are good at optimizing the coefficients in front of linear combination. So we're wondering whether we can reparameterize this as a linear combination. It turns out that we can. So the only thing that we need to do is to find the two faces, B1 and B2, that will enclose all of the data points. So meaning that B1 minus is less than X is less than B2 for all of the X in our data set. As long as we can find this B1 and B2, then we can simply reparameterize U as this functional form. And if you optimize this, the trajectory will be the bottom row of the little GIF that I just showed. It's a lot easier. Note that it introduced a constant term that will cause a little bit of trouble when we optimize them. But luckily, if we're in a QM setting, then the absolute value of energy is not as important as the relative energy. Okay, so then we move on to see whether we can just reproduce a legacy force field. So we grabbed a Falcatho, I'm sorry, there's a typo here, it's actually Falcatho rather than Alcatho dataset. So it's a dataset from open force field. It's basically just simple aromatic or non-aromatic carbon, hydrogen, oxygen datasets. And so we trained on 80% of them and we test, we validate on 10% and we test on the rest of the 10%. And it looks like we can not only recover all the energies and we can generalize outside of the training data set, but we can also do a pretty good job when we try to recover other parameters. So the parameters in a sense is the sole set of parameters that determine the entire dynamics of your system up to a point. So yeah, that's encouraging, but there are still problems, right? So one type of system that would be particularly tricky to deal with is this kind of, maybe this is, where is this? Yeah. So one type of system is a bit tricky to deal with is this small 3 and 4 membered rings. And this is actually very, very interesting from an MM perspective, right? So when we fit a Espaloma model to 3 and 4 member rings, or even if you just have 3 and 4 member rings in your system, you will notice that, okay, so let's look at subplot B. So the orange line here is the reference energy, or how GAF parameterizes it. So GAF1, GAF2, and OpenFF parsley, they're all pretty much similar. So they would believe that the equilibrium angle is around 60 degrees, and that they have associated a force constant. Whereas we parameterized it as having a equilibrium angle at around 122 degrees. So it's not that much different than 109, which is on sp3 carbon, and our force constant is slightly larger, right? So part of the reason our model is reluctant to go to 60 is because if you're training this with other molecules, then pretty much all of sp3 carbon, they will live around 109, and all of the sp2 carbon will live around 120, the equilibrium angle, right? And 60 is just a huge outlier that the model is reluctant to go to, especially because we have some sort of regularization. Already starting. So it will be very reluctant to fit to that. It'll be a model with very high variance. So find this space where the training objective, when it comes to the training objective, the sort of is to generate. Okay, so how is that the case? So if you plot so if you look at C, which is the reference angle versus the predicted angle, you will see that there's, okay, this is just crazy, right? It's not a straight line. There's no even correlation to the harmonic function. However, if you sum them up together, then you would pretty much get a straight line. That is because you have three angles, and all of these three angles will sum up to 180. So if you sum them up, although the individual component will look crazy like this weird shape, if you sum them up, it's pretty much a straight line, right? Actually, it doesn't matter how much you deviate, as long as one of your angle is between 50 and 70, and the difference between the other two angles are from -10 to +10. Then you can never ever get a relative RMSE greater than 1 kcal per mole, meaning that these two parameterization are almost equivalent. And this is actually a debate that has been going on. John told me that's open force field and elsewhere, whether we should parameterize this cyclopropane as having a 60 or 109 degree of as their equilibrium angle. All right, so encouraged by fitting results, we then move forward to see whether we can just produce a force field by fitting to quantum mechanics data. So these data sets are all on QC archive, and they're all with slightly different emphasis. So Falcatho, as we talk about, and this is the data set that we used in fitting. So Falcatho, it's more about just the limited CHO chemical space. Whereas open force field generation to optimization data set, which is the data set they use to produce parsley, is more drug-like. It consists of the few subsets that's donated by our farmer partners, right? Vehicle data set is a data set of heterocyclic small molecules. And finally, PepConf, which is, well, by its name, peptide conformations. So it's just small peptides, it's di and tripeptides, and there are also cyclic peptides. Okay. So it looks like we, like all of our test RMSE is around 1 or 1.5 kcal per mole, with the exception of PepConf. And we'll compare to traditional force field. It's always the case that we would be then by a margin. And it is especially interesting if you look at vehicle and PepConf. So vehicle data set consists of these kind of heterocyclic rings. So traditional force field would have a very hard time distinguishing different atom types, whereas Espaloma will pull the information based on its neighborhood and its message passing algorithm. So it will leverage the node identity with its neighborhood. It's a little bit more robust. Yeah, that's why we can get a 1 kcal per mole RMSE rather than 8-ish predicted by either open force field or GAP1 or GAP2, right? So in PepConf, we also did a small experiment where we used amber force field to parameterize PepConf, and there's still a very large discrepancy between amber and QM. It is worth noting that there are 6 cyclic peptides that cannot be parameterized using open force field toolkit engine for amber. So this is not a strictly compatible or strictly accurate comparison, but I would imagine that those 6 cyclic peptides would be even more tricky to deal with than the traditional than the di and tripeptides. Okay. Next, we do something even more interesting. So we're wondering whether we can come up with a force field that are trend on both drug-like space and peptide space. So basically, we took this Gentoo optimization data set and we took this PepConf data set without like too much balancing, etc. Just pull them together. And it looks like we can still do okay, although the RMSE is worse than if they have been trained on each data set individually. All right, so It's not always about RMSE, right? When people use the force field, it's okay if the RMSE is a little high, as long as it's qualitatively right. So Espaloma, if you look at it qualitatively, then it sort of preserves the quantum mechanics minima to some extent. So what we're doing here is that we have a set of reference quantum mechanics minima in QC archive. So basically, you just take the argmin of the energy and you return the corresponding snapshot, right? So these are just global minima uh, of quantum mechanics. And then we use Espaloma to start from the minima, and we use a BFGS optimizer to try to optimize away from the minima. And it turns out we didn't go very far, meaning that it sort of preserves the QM minima. Note that if you compare this experiment to that of GAF1, GAF2, and OpenFF, OpenFF did a better job at this because this particular data set is what open force field is fit on. And if you look at the KDE plot of kernel density estimate plot of GAF1 and GAF2, then you will realize that although their peak appears at a better spot than Espaloma, they have very, very long tail, meaning that they're good at a subset of molecules, but for some molecules, they just fail horribly. All right. Apart from bounded parameters, Espaloma can also integrate charge, but there is another step before we predict charges, because charges, it's not independent among atoms. They have to obey the constraint that they all have to sum up to the total charge, which is some number denoted by big Q, which could be positive, negative, or zero, right? So traditionally, people have been encoding this with just another loss term, but you are not observing the physical symmetry exactly. Instead, we can solve this constraint optimization, use just Lagrange multipliers, and come up with the analytic solution. So we plug this equation 35 into our Espaloma model. It's basically just saying that, okay, you need to predict two free parameters, E and S, which is the electronegativity and the hardness, and then you would come up with the independent Q hats, and that's what charges. And the better thing is that if you train the charge model and the valence model jointly, then it would do better on each task, meaning that there is some level of transfer learning happening inside the model. Oh, this is also worth noting that if you look at our charge RMSE, then it's around 2 or 3, it's around 0.02 or 0.03 kcal unit charge, which is comparable to the RMSE between the Ember toolkit assigned and OpenEye toolkit assigned AM1 BCC charges. All right, so next step, we scale this up to protein system. And we use the dumbest protein system, which is just alanine N system. So the first thing we observe is that the parameterization is more or less stable. So A is just ACE a la an NME system, and B is ACE a la 3 NME. And we also examine like up to 10 alanines in subfigure E and F. It looks like the bond length and the charge assigned are all pretty much stable. They stopped changing after a few atoms, which is reasonable, right? So they theoretically cannot change because of White-Fellner Lyman equivalence. And moreover, if you look at its parameterization and energy evaluation time, you'll realize that up to a point, it scales linearly with regard to the size of the system. And if you're using a GPU, then the parameterization step almost is constant with some fluctuations. And so the energy evaluation time is exactly the same as any other force field. It's a lot faster. It's around 2,000 times faster than the Schnatt. I've tested on my broken MacBook Pro versus their their benchmark test on their Tesla V100. And the parameterization time is always less than a second, even on CPU, as long as your protein is less than 500 residues. All right, so if you still remember the experiment where we train on both both open force field generation to optimization data set as well as PepConf, you'll realize that we can parameterize this protein and this ligand simultaneously. It is perhaps the first time people can do something like this, right? And we haven't yet tested the quantitative behavior of this kind of force field, but at least it's stable. So we will leave the quantitative investigation to future studies. And then finally, we can do some even more exotic things that have never been done before, namely parameterizing this very heterogeneous system like this covalent adduct, right? So previously, because you have a separate small molecule force field and a separate protein force field, it means that it's almost impossible to determine the parameters around the bridge of the covalent adduct. But in Espaloma, because we don't care about whether you're a protein or a small molecule, you're just a graph. It can parameterize these kind of stuff very easily. So for the parameters that are far away from the bridge, you'll see that it's pretty much just the same. And again, by Weisfeld-Lehmann equivalency, after you are 3 or 4 bonds away, it theoretically cannot change. All right, so future work, part of the step that I'm very excited about is to expand this as a class 2 force field. So you can sneak in your coupling terms or higher order terms, and they can all be expressed as attributes of angle or torsion or bond. So this has all been implemented, but we'll just need more extensive experiment to see whether we can actually bring the performance even better. So that's it. Thank you, and I'm happy to take any questions. All right, thanks.
Thanks so much, Yuanqing. Any questions for Yuanqing about Espaloma?
I have a lot of questions, but
Sure.
the main one is, so you're learning to build a force field that is useful for ligands from QM theoretical models, right? Or previously existing force fields.
Right. You can do either. You can either build a force field based upon data from previously existing force fields, or QM calculations. Either.
When you're learning I guess when you're learning a force field that also includes the protein, obviously you're not doing QM on the protein, right? So where are you combining those two, or are you just then separately doing learning from like Amber or something?
Okay, so there is this data set called PepConf, which is just peptide conformation. It's all QM calculated. So it's only di and tri peptides. But if we learn on that, because of the inductive bias of a graph neural network, it doesn't know whether you're in a small peptide or in a large protein. So we can generalize the parameters to like a very large protein.
I think one of the things that wasn't mentioned here is that the Leonard-Jones, and for the most of the experiments, the charges came from the open force field. And that the typical way of getting valence terms like this, bond lengths, angles, torsions, is to extract them from small model compound quantum chemical energies. Obviously, to really get the other parameters nailed, we need to extend this into physical simulations too, where you're simulating liquid mixtures or other kinds of condensed phase systems. And then ultimately, you'd like to be able to match things like NMR order parameters for entire proteins too. So these are things that could happen, but obviously require much more expensive computations than just computing quantum chemistry.
Right. I guess my thought is like, there's like an emergent property effect as you move up the scale of phenomena, right? So I guess the concern is, can you accurately recapitulate protein in solution behavior using terms learned from quantum mechanics?
That's a great question. And
yeah, I guess that's what you're trying to figure out.
Yeah.
I mean, this has sort of been the hypothesis for molecular mechanics force fields for a long time, though we know that's not true, which is why we include experimental data too.
Right.
But surprisingly, that has been quite successful for
Right.
biopolymer force fields. But you're absolutely right. Every time you coarse grain anything away, then you're liable to miss some of the things that you need for getting these emergent cooperativity phenomena, or implicit polarization of charges, or any of the other things that we might be missing in larger systems. There's especially important missing nuclear degrees of freedom, right? So even if you had the perfect quantum chemical force field, you would not be able to recapitulate a lot of condensed phase properties, especially those that involve protons or hydrogens, because they're so light that they have significant quantum nuclear behavior. And so you would need to do path integral simulations at that point. We don't want to afford the extra expense of that. It's very, very expensive. So instead, we try to build that in by doing condensed phase simulations and correcting them. That's sort of the general strategy for open force field and others.
So, oh, yeah, you say here, joint. I was going to ask, how do you learn both from a data set of the peptides and data sets from the ligands? But that's what
they're
this
just
joint
graphs.
thing is. Yeah.
Yeah, you just put them together.
Yeah.
It's a large data set.
Yeah, that makes sense. Cool.
Yuanqing, I mean, you know that I love all of this, and I've already had a great degree of success with this, but I was actually going to ask you a couple of questions. One, how do you see this like being expanded to things like to more like, I guess, accurate, quote unquote, physical molecular mechanics models like polarizable force fields and stuff? Is that something that you think is would be in the future for Espaloma, or do you think you would go in a different direction with?
Oh yeah, definitely. So before polarizable, I think coupling and higher order is more near-term goals, because a polarizable, when you run it's correct me if I'm wrong, John, but it's fundamentally slower than a traditional force field, isn't it?
Yeah,
Right?
by like
Whereas
10x at least in my experience.
Yeah. Whereas if you just parameterize your second your coupling term or higher order term, then it should be comparable to the existing data set. And we don't need any modification of the code, basically. You just need to write a new functional for the geometry, and you just put more parameters there. Yeah.
The valence terms that appear in class 2 force fields that are all of these couplings are, order n, so they don't really impact the speed at all, even for large systems. It is possible you can use point polarizability through Drude particles, and they claim that it's no more than a factor of 2 slower. In fact, it's probably like 40% slower if you're using the new charm Drude force field. You also don't need Drude particles everywhere, so that cuts down on it maybe only certain heavy nuclei require Drude particles to get accuracy. So these are all things you can explore with this very easily by refitting the potential over and over again. This was the real bottleneck for exploring these before, is that we just didn't have a way of hand tuning 50 different force field variants by 50 different graduate students in parallel.
Yeah, no, and that makes sense. I mean, it's just it's a harder. Now it's possible to do other things. I was also thinking in the context of amoeba and applying it to like the functional forms for polarizability, or whatever Joshua Rackers at Sandia National Labs is building to remodel long-range interactions.
With Hippo, yeah. So
yeah, Hippo, thank you, yes.
There are certain things that it can easily be extended for. So predicting point polarizabilities seems like a very easy thing to extend Espaloma to do. Predicting like multipoles in reference frames is going to be very hard though. So, I mean, it might be possible, but you need a good basis set for being able to predict that.
Yeah.
The other possibility though is that a lot of these, like a lot of the models that are next generation electrostatics models, can also deal with charge transfer, which is kind of cool. And that you can predict like essentially an extension of the electronegativity and hardness model that Yuanqing is already predicting for the charge model, and also extend this to moving charges between molecules in space based upon geometry dependence. So there might be ways to support these kind of more advanced MM-like long-range charge modeling things in the future without having it be inconsistent. So maybe we don't need the craziness of like fixed multipoles in space and can get by with other things instead.
Yeah, it makes sense. Actually, that brings up what was going to be my second question, which was, do you think that there's a way that this could be built towards doing QM-MM-like calculations, where instead of having to do a whole QM calculation on an active site and then MM around it, you could have different levels, different degrees of accuracy around to be able to do kind of QM style reaction calculations to observe phosphate transfers and stuff like that?
I think John might be able to answer that question better.
Yeah, that's a really interesting question. One of the nice things is that you could, in principle, I mean, there's no reason you can't use Espaloma to build multi-resolution force fields that are all compatible, right? Because if you're trying to match some quantum chemical targets or some larger targets, then and you're using different parts of Espaloma or predicting different parameters for different levels of resolution, that's all totally possible. You just have your loss function that you have to express what you want to achieve. So I think that's something that none of us had thought of before, but could be very viable in terms of trying to predict parameters for multi-resolution models, where you might have expensive polarizability in one site in one region, but not in others.
Yeah, also because I was thinking, because it's fully differentiable and graph-based, you could build for different atom types on the fly in the middle of a simulation. So if you can find a way to reassign atom types at some semi-regular intervals, it would be a slowdown, but I wonder if it would be faster than your classic QMMM slowdowns, which are, horribly, horribly inefficient simulations.
So right now the graph is fixed during the entire simulation, right? But you're saying, what if you could make the graph change during the simulation?
like mutable. Is that a possibility?
I mean, it is possible that you can use it to reparameterize on the fly, right? This is one of the nice things. Perses was supposed to be able to do, or is supposed to be able to do, sampling over chemical space by allowing us to change the chemistry of the ligand in the binding site. And you need a very fast way of assigning new parameters that way. But you could have graphs that have edges depend on spatial proximity too. I guess that's a possibility, where the character of an atom can change as it's undergoing an SN2 reaction. We hadn't thought about that either, but that could be something that's possible. But that would require extensive changes, I think.
Yeah. No, it's a lot more work, but I just got excited about the idea of like being able to model like ATP transfer and stuff. So I was just curious. Thanks.
I have a question. Have you considered doing more flexible functional forms for your energy?
Definitely.
Like classical force fields are, they're pretty well fit to try to reproduce energies with a very minimal fitting. But obviously, if we're letting the machine do it, we can provide a little more flexibility maybe and get something more accurate without kind of overfitting like we do on a full machine learning model or something.
Yeah, I really don't see like the need of keeping all of these harmonic functional forms.
Right.
As a matter of fact, they cause us more trouble than anything, right? Like everybody has been just doing like Annie or Schnatt, they just have this kind of RBF type of thing. I don't see why we can't do that. And you can still thanks to the flexible functional terms in open MM, as long as it is just the function of your R, your little bond length or your angle parameters and angle values, then it doesn't matter how sophisticated your one-to-one function is. You can always stick them into open MM, so it wouldn't be too much of a slowdown, and it will still scale linearly.
Right.
So splines are accessible in OpenMM. That's what could be one possibility, but we are like for using for the torsions, it's difficult for us to do that well to fit a torsion profile accurately. So that's one of the hidden things here, is that if you're using the periodicity of 1, 2, 3, 4, 5, and 6 cosine functions, like learning the coefficients of those you need can sometimes be complicated. Maybe there's a better representation that's easier to learn and interpolate between different atom types. So that's still one of the challenges is what are the right basis sets to use so that optimization and learning and interpolation is not crazy.
Yeah, I expect that some of the trouble in training this is because of the lack of flexibility. So you probably hit these regions where your loss is steadily decreasing maybe, and then all of a sudden some other part of the field starts messing up because of the parameter, and then your loss just starts jumping up. And so it probably has these kind of crazy kinks in it that make the gradients really kind of jumpy for it to train. It makes it difficult training, I'm sure.
Yeah. So this is exactly what we have observed, right? So if you're thinking about this, if you think about the information bottleneck, then you have a shitload of parameters at the beginning, and they are all pushed towards this like a few numbers, and then that would be expanded to all of these energies. So it's just asking for trouble. Yeah. So in Schnet they did a like the reason why they use RBF everywhere in all of these machine learning potentials, although like the single number can already represent the bond length, is because it's just a lot harder to optimize the model. Yeah, if we can get rid of harmonic terms, then that would be great.
Yeah.
Sorry, I have one more question, Yuanqing.
Sure.
It's okay. Yeah, it's basically, I was just thinking, because you were talking about how, I mean, obviously this works really well for biopolymer force fields and you've trained them against them. But one thing it just occurred to me was that a lot of molecular mechanics force fields have this limitation of working really well for either folded proteins or disordered proteins. That's kind of like a limitation where it's really hard to model like IDRs and IDPs and these proteins that never fold, quote unquote. And I was wondering if you guys had any way to, it would be cool if there was any way to compare how well you guys do against these force fields that are trained on being able to do one or the other and specialized. Because if Espaloma can do both really well, then that's a really unique and awesome way to model these folded unfolded complexes that occur like all throughout biology and are really attracting a lot of interest in like age-related research right now.
Yeah, I don't think we ever thought about this at that level, like that, that granularity. I don't think, but yeah, it's definitely an interesting direction to try. Like the only evidence we have right now is just how well it works, like how stable it is and how it works on the tri and dipeptides.
Yeah, no, and that makes a ton of sense. I got really excited because it's like a huge limitation of like if you want to model like a kinase IDP complex or any kind of complex where you have a folded and unfolded protein in general, there's no real force field you can use that will make you be like, okay, I probably trust this.
My takeaway from all of that is that there's missing effects like point polarizability that are just responsible for the failure for a single fixed charge force field to be able to model both states. And that by simply figuring out what's the missing force field science without adding too much to the expense, which we should be able to do now with Espaloma, you can do those experiments very rapidly. So I think the key is what is the missing physics that allows a single force field to treat both accurately, and then how can we do those experiments with that enabled by Espaloma in rapid design and evaluation cycles? I think that's probably the more likely solution. All right, thank you. That was great.
So final question. It's okay, like, is everybody okay with like me putting this video on my documentation website with all the questions? Is that okay, or I should just cut the questions part?
No objections.
Okay, all right. Thank you.
I'm sorry, we're shortchanging Alex now, but you can just talk slightly faster.